All right, and let's ready to rock and roll. Okay, first of all, obviously, oops, cover mic. Um, Jeff Goff, aka DrForr. Um, and if you're looking for machine learning, you come to my talk. If you're looking for something else, then I suggest moving on. What we're talking about, first of all, obviously this is Perl 6, not Perl 5. There is a fairly well thought out, supposedly. I haven't looked at myself, binding for Perl 5 for the TensorFlow library, but this is my own binding, trying to make things look a little bit more Perl 6-ish, because there are a lot of little features that we can implement in Perl that you don't need to do and can't do in Python in a few cases. So it is more of a Perl 6-ish attempt to make the TensorFlow libraries look more Perlish. My GitHub account. This is all on my GitHub account right now. You can take a look at the URL from there. It's all there. The talk will be up within a few hours, hopefully, or tomorrow. I also have a very, very unused blogspot website, the Perl Fisher, reference to a what is it? Not Bizet, but play. I have to like. All right. What you'll need to know in order to actually get both TensorFlow and my libraries working, first of all, obviously you'll need Perl 6. Well, I have my laser. You also need Python, unfortunately in this case, but the TensorFlow libraries, while they are great, the Python libraries are highly evolved and do a lot of work to implement operator overloading and caching and object communications on top of the TensorFlow library layer. So we need to use Python to do the work. Obviously, you need the TensorFlow libraries. They are separate, but if you are working on this, I would advise installing them in a certain order. I'll cover that in a few minutes. And the last thing, obviously, you will need is the Perl 6 binding for TensorFlow. Okay, so a little bit of history as to what, a little bit of the background as to what TensorFlow and machine learning, where it came from, and where it's going in the future. Way back in the 1950s, we started out with a incredibly strange beast called the perceptron. This is, to my knowledge, the only instance that was ever created of this. It's impossible to see at this detail, and I apologize, but the idea was it was to be a mimic as best as you can do back then, given the limitation of 1950s computing. And in this case, it was not so much computing as analog. The idea back then was that you would take an image, say, of a cat, digitize that down to a very, very small frame, maybe 10 pixels by 10 pixels, each pixel being a cadmium sulfide photocell, and shine that through there, picked up on the photomultipliers in the background, and cascading through the neural network, all hand-wired with potentiometers and motors to do all the quote calculations. Now, mathematically speaking, this was a okay model until, and the reason that this was the only one ever built is because of a guy named Martin Minsky back in the 60s, when he pretty much torpedoed the entire idea. if when he found out through research that even though this cascading flow multiplier and cascading neural network was wonderful for certain problems, it couldn't solve a simple XOR problem. It got sort of missed in the calculation. So, this is what caused the infamous AI winter. It started up in the 60s, and Minsky Paper's paper came out in the late 60s, and pretty much torpedoed AI research until Hal, in this case, or Myson, the export system in the late 80s, early 80s, just before I was in college. This, in this case, is a symbolic Lisp machine with the infamous Space Cadet keyboard. You'll see it's got a super meta hyper keys. I'm not kidding. That's super, that's meta, that's hyper. Aside from the 2 shift keys. And unfortunately, there's no pedals on this model. I've also seen versions of this that have a separate organ keyboard to get the rest of the keys in. So this was an expert system where you would end up, where the idea being that a doctor could go in and type in, could answer a series of diagnostic questions, and this machine, on the basis of Bayesian logic and feedback, would diagnose the patient. And the most famous one that came out was probably Myson, and it was roughly 80 to 90%, 90 to 95% accurate at diagnosing a patient. But of course, if you're doing medical work, 95% isn't all that great. You want ideally 99% to 100%. So that idea kind of got shelved. Later on, we came up with the idea of neural networks, which is kind of harkening back towards the original perceptron in that it has several layers of wiring. Here would be your input coming in from, say, our old cat image. This time, we're now in the 1980s and 1990s, so we have CCD panels, and you can have color images going onto a virtual retina, which would be this layer over here. And that cascades through the, quote, brain, unquote, through this passage right here, a randomly wired neural network. And each of these hidden layers would take the input sum, would take the inputs like this and this and this, sum that, apply a convolution function, and activate the output. And if the neural network did the right thing, you go in and activate and increase the bias of the nodes that did the right thing and return a strong result, and decrease bias on the nodes that return the wrong result. So there's a feedback process here. That's not indicated in the diagram. You have the network here that does that, and after each step, when you train, this comes from the output and is propagated back through the hidden layer through a convolution function. And this model worked up until and sort of lingered up until 2015 when TensorFlow came around, courtesy of Google. And this is what we're working on and talking about today. I promised in the abstract that we would design a 3-stage or 3-node neural network. I do have to caution you that the term neural network in this case is a little bit different than how things work in a classical sense, and I'll talk about that as we go on. In our case, the neural network, quote neural network, is comprised of 3 nodes, a top summation node that takes inputs from the weights of the neural network, which in the old model, in the old model, the weights would be inside the hidden layer of the neural network, displaying the this is how it does the quote computation. And in a classical neural network, this is where all of the magic is hidden. It also has a set of biases that get passed in from training, and that is part of the feedback loop that you get from the output, correcting the data, going back and correcting the biases on the hidden network. So that is the feedback process that you get. Now, I will warn you in advance, because while TensorFlow is large and libraries are large, the way I have had to wrap them in Perl 6 means that I can't easily bind one object directly to one Python object directly to a Perl 6 object. That's not quite the way that it works with TensorFlow, and I need to talk to Nina, about the creator of inline Python, about some possibilities to update the object, how to specifically be able to return a typed object from TensorFlow back to the Perl 6 layer. I have some workarounds that I can show you, but they are somewhat ugly. Specifically, I have to get the type of the object, the JSON data, and unpack that, send that back as a string instead of as a proper Python/Perl 6 object. But the good news is that the process isn't all that bad. First thing about setup. This is also in the README, detailing steps. The important thing here is if you're going to play with this, by all means, okay, obviously you need these bits. Perl 6 being my Python module that you could get from Zeph, but that you can get from Zeph, which is module star. TensorFlow, which is my module, and of course Python and TensorFlow libraries. The important thing to know when you're building this is to make sure that you use PyEnv and do all of your building, including Perl and Python and TensorFlow, inside that environment. Because that is how PyEnv is roughly the equivalent of Perl brew/Recruiter brew. So it lets you switch out libraries, and in this case, it will let you take the TensorFlow libraries, link that with a single Python instance, like an inline C binding or XS in Perl 5, and do that. Again, it's all covered in the documentation, and it's all now up on GitHub. So you can, by all means, correct me when I'm wrong on such things. So, the module is called TensorFlow. So you might wonder what a tensor is. Well, thankfully for us, you don't really need to know about what a tensor is. In this case, what it really is simply a big array, a multi-dimensional array. 2, 3 layered, 2 or 3 dimensions. Here, again, I'm using Perl 6 syntax. These are just the equivalent of QW in Perl 5. So I'm simply creating a two-dimensional 2 by 3 tensor. 2 entries here and 3 entries on the side. But you really don't need to know that for the basics. Tensors are a high-level API that I haven't gotten around to being able to bind. Now, all right, so let's look at some of our actual code here, actual numbers, actual data. TensorFlow, in this case, is a singleton object, hiding one instance of the inline Python interpreter. So what we do is create a TF for TensorFlow, obviously, and it also happens, not by coincidence, to match what the TensorFlow docs in Python do. The idea that I wrote this module with is that you can take the TensorFlow documentation, add $signs in front of the TF, do one or two Perl 6-ish things, remove some arrays that you don't, remove some array brackets that you don't need, and you have your Perl 6 code. That's the general idea. $pi here is necessary for the print functions because what I've done is separate namespaces as well. TF is the main TensorFlow namespace. There's also separate NP for NumPython, NumPy, but I haven't done any work with that just yet. $pi here is the main namespace the main namespace for functions such as print and print sort split in Python. So that's how I separate the layers. And I show you exactly how closely the translation is from Python to Perl 6, with a few exceptions. So, how do you actually use the TensorFlow module, you might be wondering. Well, the first thing that you want to do is set up your training data. In our case, as a few simple Perl scalar, a few Perl arrays. You then set up a classifier function. This is essentially how you would, where you would write, say, your function to determine if an image is a cat or not. Next thing you may have some data inside you have a set of biases, as we talked about, that you need to feed in. So you set those up. But the most important bit here is the feedback loop that you set up. So once you evaluate how close the image is to a cat, you then can use that image against the data set and train that to feed the image back, to feed the data back in. Now, I would love to be able to show you a cat classifier, but the code would easily go off the screen and be in a type font size no one here, including me, could read. So what we're going to do is do a very simple mathematical problem. Try and solve an equation. If there are math geeks out in the audience, you can probably solve this within a few seconds. Specifically, here the value w is -1, and the b here is 1. It's easy for us to solve. No problems. If you do this you can use, say, matrix algebra or linear programming to solve that in a computer as well. But the thing is, we want to solve that using TensorFlow techniques. So what we have to do is, first of all, tell the computer what the equation is that we want to solve. And this works for any sort of equation. This is not just a technique like linear algebra or equation manipulation. This is a technique that works with any data set. What I'd like to analogize this to, courtesy Charlie Strauss, is a high-dimensional ski slope. This equation here will be the contours of the slope. W here and B are the actual height as you change the slope. So the ski slope is essentially a slalom course. And you'll go up and down, and after every iteration, the computer does this for you. It shrinks one slalom, boosts another slalom, maybe makes a pole at this, or two ski poles on that side. Your training data here, these numbers, are skiers that are being sent down the hill. Try and find the lowest point in the hill, because the lowest point is where the solution lies. Now, because of the way TensorFlow works, these equations can't be of arbitrary size. This right here is just a four-number equation, but you can do anything up to thousands of variables, and it will still do the optimization for you. What the TensorFlow libraries mainly do is do the feedback process for you, and what it will do is take this value and shard that across multiple cores, multiple CPUs. It's essentially the old MapReduce Google thing writ large. So it handles the MapReduce for you. It handles collecting the data. It handles doing feedback. So we have some more Perl code here, thankfully. We'll take our x. We'll take the x and y position. These are initial positions of each spheres on our slope. X of 0, y -1, x1, y -2, and so on. We position those on our virtual plane. Then we have to tell the computer how we classified, how the ski slope works. So what we do here, ignore this for the time being, and focus on this. This looks like a calculation. Like you would take a value slope and a value x and get back a single scalar value. That's not the case here. A lot is going on behind the scenes in this. What's happening is the TensorFlow libraries are creating a graph, which you saw a few minutes ago. A calculation graph or an AST in Perl 6. So out of these variables. So instead of having just a variable times variable plus variable, you're creating a variable with a multiplication node, and that multiplication node has a addition node down here, and that is what gets passed into TensorFlow. And TensorFlow then takes that diagram, plugs in data for, say, the x-intercept values here that you have, plugs those into the $x that you have here as a placeholder. And again, this is very close to how the Python code looks. Specifically, if you eliminate the dollar signs, get rid of the my, you have the Python code. Oh, minus the semicolon, of course. Get rid of that. It is that close to the Python code. So when you are looking at code from, say, from the machine network MNIST on the TensorFlow site, you can translate that from Python back to Perl 6 with relative ease. The placeholder variable, again, is meant for your training set. If you want to create, say, a training set for cats, you would create a placeholder, my$cats equal $tf.placeholder parent, and then give it a type of TF image or whatnot. You can train based on that. So the placeholder here is essentially where you insert your training set. The seed data that you give it, this is where you want to start looking for the solution to the equation. Because even though we actually know the answer is -1 for the slope and +1 for the intercept, we have to give TensorFlow something to start with. If you're doing this in a proper philosophical manner, you will want your neural network to have no biases and to generate these numbers completely at random. So that way you don't know where the neural network starts, and it has to work its way down and find the values. But this is from a test suite, and you want test suites to be repeatable. So we're simply coding in here a 0.3 and -0.3 value for these variables. And I deliberately switched the signs to make it a little bit harder to work with. And again, down here we have this sign is a variable, and these are our biases from the neural network. This is what we feed back to the hidden layer in the network. The biases are what we feed back, and the weights are what accumulate as TensorFlow works through the equation and iterates through that up to 1,000 times to find the solution. The feedback portion. This is, if you remember, we have in the traditional neural network, we have the layers of input, the hidden layer, and the output layer, and the feedback from the output back to the function. This is how you tell TensorFlow to correct the solution. Because the first time it's going to do the calculation, it's going to run this calculation, and I'll show the math a little bit more in more detail later on. It will run that calculation, and obviously 0.3 minus 0.3 times x minus 0.3 is not the right solution. So you have to tell it how to track, how to correct for the mistake that it made. And how we do this is a little bit more Perl 6-ish. So how we do that is we tell TensorFlow what the difference is between what we expect and what is actual. And in this case, what we do is the model here, the model output that we got, subtract the new model, subtract the old model, and we square that value. That way, what happens, if you have, say, a value of 0.3, you square that, you get 0.09. And so that way, small changes get minimized, and large changes like 0.9 squared goes to 0.81 squared. Large changes stay large. So you are trying to minimize and converge on a solution. And this is written in more Perl 6-ish style. You'll note here the Unicode squared over there. And you'll note here as well the bracket plus. This also is a graph like the slope calculation that we had beforehand. So this here has a computation graph behind that, plus the reduce plus operator here, and subtraction and the squaring operation. Those are all creating a graph. So this is not an actual calculation that you would run and do the math on yourself. This is what you pass off to TensorFlow to tell it how to do the math and narrow down that. If you're not used to Perl 6, the square bracket plus sign here is essentially taking the output from all of our training sets, all of the values of y that we had in our list, reducing all of those, and creating the sum of that. So the sum of that becomes our total loss that we then subtract from the neural network. So, how do you actually do the training? Well, this step is not yet doing the training. We are setting up the conditions. We are telling TensorFlow how the skiers are going to move around on the slope. In this case, is a simple gradient descent. Unfortunately, I don't have a handy graph for this, but if you visualize a sine wave going gently downhill, you have a skier at the top, and the way the gradient descent program works is it finds the easiest gradient down. So it will find from this hill this way, tilt down, move down that way, tilt down, tilt up, tilt down, like so. and do that for you, do the optimization for you. And the 0.01 is just how much it will change the gradient at each step. So you need a lot of iterations. So what we tell TensorFlow is we want to use this optimizer, and we tell the optimizer to minimize based on the loss function, which we created back here. And then the fun happens. We take the model that we have. We give it our training data here. We have our trainer and our training data here. So our X value, our X placeholder, our training data, Y and Y training data for both coordinates, of course. And then what the run does is it runs this, in our case, 1,000 times, loops over the data set 1,000 times, each time taking the X and Y values, computing our result, adding our correction, or actually subtracting the correction from the data set, and we eventually converge onto a final number down here. So at the very last, we get out the final data from the correction, and we get back our weights, our biases, and current loss. So, and finally, on the Python side, we do the printing of the data. This is a little bit sketchy right now in the code, if you take a look. This is where things go a little bit haywire because of the way that I'm having to send the data back from Python. So this isn't quite yet finished, but it will work if you use the wrapper correctly, and I can show you a little bit of that in the code later on. Down here, what we'll print out is the data set, and luckily for us, it actually gives almost the right answer. It's saying 0.099999969 minus, and B of 0.99999082. Again, TensorFlow is not solving equations. It is iterating to find a solution. So it just keeps iterating and iterating, and it will get close to the solution, but never, of course, right there. But, 5 figures worth of accuracy, and your loss is, and your actual loss there in the training set is 11 decimals down. So that's pretty accurate for 1,000 iterations. If you try this at home, these numbers will be different, of course, because we all have different CPUs and different, well, most of us have different, some of us have different CPUs, but we all have different computer loads and random number generators, etc. Those will all change things. Those will all change a little bit. So that's the general. That's in a nutshell the general idea. You take a function that you want to optimize, whether that be a cat recognizer that has a way to detect eyes, whether that be a capture recognizer that has a way to detect numbers, and you use the TensorFlow model and continually iterate over your training set until you get a final answer. So that's the process in a nutshell. There are higher layers of abstraction that you can use. The Python code lets you use closures and lets you use callback functions. I haven't gotten to that point quite just yet. I'm glad that I got to the point where I have a session to work with for the code. So, to help visualize this just a little bit better, here's roughly what's happening. Here's roughly what's happening on the inside. And again, remember that TensorFlow is doing all of our looping here and doing all of our calculations, and all of our map reduces for us. So you remember at the start we assign a weight. We assign variables to a weight. So we assign here our initial process, our initial starting values up here. We create our training values, and then all we're really doing is running this loop over our data set. The gradient descent optimizer is a fancy name, but all it's really doing is computing the average of the data sets, squaring the data sets, or computing the squared average of the data set minus the loss, and feeding that value back in. That's all it's really doing. Yes, it's doing it very fast, and it's doing it over multiple cores and multiple CPUs. So that's what's going on there. Just to go a little bit more into depth on that, let's break that down just a little bit to explain why it's important to get some of the narrowing aspects. Here's how the equation here that's going into the optimizer, and here is our data set. And again, if you do the math in your head, like so, $W here turns out to be -1, because you want to take these signs here, flip those, and then add 1 to the data set. Add 1 to all the values, so your bias here becomes 1. Right now, what's happening, if you run the calculations with the first data set, you get this back. Instead of 1 is 0, instead of 1 is 0.3, instead of 1 is 0.6, instead of 1 is 0.9. When we take that value and square that to make the values that are close to 0, those go even closer to 0, because those are more accurate. Values that are outside, values that are larger, are more error prone, so they get narrowed in just a little bit, but not as much. So we're trying to converge on a solution that way. That is part of the equation. So then on the next iteration, what TensorFlow does for you automatically is takes the average of those values, adds that back into the old data set, and creates a new data set. So TensorFlow has already a large library of applications out there with a lot of Python code. So you might want to know how the Python and the Perl code right now stacks up. Well, it's pretty close, as you can see. Take the $signs off the code. Take $signs off. Take the money off, and it's pretty close. Working your Python interpreter. Wait a minute. Python doesn't do Unicode operators. So let's replace that with a squared. Slight problem: Python won't let you overload exponentiation. So, and that is needed for the graph. So we can't do that. So we'll call the square function on that, which returns the square of the comp. Remember that the loss here and the model are both graphs. Well, Python doesn't let you do custom operations, in fact, at all. So we have to replace that with the Python equivalent and tell it to do the map reduce using summation. But aside from that, it's pretty much the same thing. Here's a quick guide if you want to get in and look around and see what's going on. The variables, I've stripped off the braces from Python for convenience sake. the tf.square I replaced with, I let you use the Unicode square operator. The reduce sum, I let you use the Unicode, let you use the Perl 6 reduction operator by summation. And finally, I've already created all of the basic Python objects that you need in Perl 6. So you have a train package down here. I created that already. So I use tf.train. It looks the same as in the Python code. And we take a look here at more actual code here, and you see how closely these line up. I mentioned before about the brackets here. Those are gone. Python requires you to give it a dynamic type for your placeholder or variable. With Perl, you don't need to do that. That's gone away. All you have, the linear model over here that we're calculating. This one thing that has to stay the same because you have to tell what type of placeholder is. I might let you later on add in a value like 1.2 or -1, and I'll let that call the internals for you. But you'll see reduce sum, square is the square operator there. So I've graphed that as well. X train and Y train, those in Python are array reference. In Perl, those are just plain old arrays. So it's not quite one-to-one, but it is close. There are a few things that I can do later on with, say, TensorFlow has a notion of a session that you open, that you start up and shut down. And this probably can go away as the library evolves, because there's no real reason to not have, say, a class to handle session or even a keyword, but I'm not going to go there to handle sessions. That should be out there in one. That right there should be out in Python because otherwise it's illegal. I haven't quite figured out how to get this construct to properly render into Perl 6. So that's why you see some disparities. But again, for char 1000, for I from in range of 1000, that's again from Python Perl, straightforward one-to-one. What I do with the, let's see here. At the very end, we have the session return has a brace. This construct, I'm not quite sure in Python how to interpret that in Perl. But I'm trying to make sure that this stays relatively one-to-one, so people other than me can go in and hack on the source and add in their own optimizers, add in their own functionality. So I'm trying to keep that relatively one-to-one so that there's not too much change from Python over to Perl code. Running up on time for questions, if anyone has those. Aha.
How's the performance?
Performance actually is pretty good because one of the benefits of using inline Python is all we're doing is calling the Python iterator. So this loop right here, is the only thing that is somewhat slow, but I don't notice any change. I don't notice any change on my box between the Python and Perl in terms of runtime, because most of what's going on is going on the Python side. And if and as I start to work on the higher level libraries, the performance should improve even more. Okay, one more.
Is there any plan to port Keras to Perl?
To port.
To port Keras, the wrapper around TensorFlow and Piano in Python?
Okay. Any plans to support the Caro wrapper? I'm actually not sure what that is. We'll need to talk. Okay. And okay. I'm getting the cut. I'm getting the cut sign. So thank you very much. And if you have questions, then by all means, afterwards, I'm here. Thank you.